Alright, so on page 54, we're going to tackle a few problems. The first one is not central limit theorem. Second one is central limit theorem. So we're going to see the similarities and differences between the two ideas. All right, so it says find the probability that the score is above 140 given that the mean is 143 and the standard deviation is 29. All right, so this is just a generic standard normal curve graph that I created 2 videos ago. I forget. But yeah, we would have 143 in the middle instead of 0. And then we would be subtracting 29 and increasing by 29 in order to give us our benchmarks. All right, so let me get my tool on here. So 114, that's 1 standard deviation below. And 172 would be 1 standard deviation above. Let me just reference what the question's asking. Above 140, okay? So I don't know precisely where 140 is, but I do know it's going to be just south of 143. That is not my line draw tool. Well, actually, I had it on. That's weird. It was so off that the app could not recognize it as an attempt of drawing a line. That's what nerve damage will do, I guess. Anyway, so we're looking for the area, so that's a normal CDF. 140 to something resembling infinity, not really, but you know, something that we're going to use in place of infinity, to with a mean of 143 and a standard deviation of 29. All right, and again, the setup in your calculator may be slightly different. You might have the wizard, but it's still the same values in the same order. All right, so second vars normal CDF 140. Well, I had used like 100 for some of the other problems that we did, or 10 or 20 or something like that. But those would not be large numbers anymore because our benchmark here is 140. So let me put in like 1,000. Again, arbitrary value, just something big. All right, and then I'm just going to choose something bigger. All right, so maybe I'll get a little silly here. I'll do 1001. Decimal is the same. I'm only going to 3 significant anyway, so we're looking at 0.541. All right, which corresponds with the graph. Makes sense, I think. We have a little bit more than half of the graph shaded in, and I have a little bit more than half of the available area. All right, maximum possible is 1. Half is 0.5. This is a smidge more than that. All right, now the next one is saying find the probability that the mean score, not the score, the mean score, so let's highlight that, is above 140 given that the mean and standard deviation are this and that, and n is 100. All right, so the way the central limit theorem works is instead of going individual by individual, you go group by group. All right, there's a lot of applications for this, but the idea is basically that if you can draw conclusions about entire groups, then it's going to be more efficient than drawing conclusions about individuals. All right, so if, for example, I was looking for, you know, this is dealing with weights of individuals, but let's say I'm a quality control inspector, and I wanted to make sure that the product that I'm producing is within the appropriate parameters. All right, so, and let's say if that is related to weight, you know, the item is supposed to be 5 pounds, for example. So instead of weighing one item at a time and seeing if they're around 5 pounds, what I could do is weigh 100 items and see at a time and see if their weights are around, collectively around 500. All right. Yeah, there might be one or two that are off in there, but the idea is that if the collective weight is in the neighborhood of 500, very, very close to 500, then you can expect that most, if not all of them, would be around that 5 pound mark. All right. And so that's the basis of this concept. All right. But mechanically, we go back to formulas. So that's one thing you can kind of rely on, is that if you're looking for mu sub x bar and sigma sub x bar, there are formulas that you could use, but obviously, this is math, right? It's always, you could use the formulas, but if you understand the underlying concept, it just makes everything a lot more manageable. All right, so 143. The standard deviation was 29. The n value was a clean 100. So the square root of 100, which would be 10. So sigma sub x bar would be equal to 2.9. All right. So in my normal CDF, it's going to be generally the same structure: min, max, but instead of mu and sigma, mu sub x bar and sigma sub x bar. That's for the central limit theorem questions. And so the big question is, how do you know it's central limit theorem? Just go back to what I highlighted. The probability that the mean score is above 140. And there's an n value that's given to you, compared to the question that came before. It didn't ask about a mean score, and it didn't give us an n. All right? So that's really all there is to it. I mean, we do have to do the work now, but it's going to be a lot more manageable. All right. So now 143 is still going to be our middle value in our graph. Let me get my draw tool on here, or my editing tool, whatever it's called. But now, instead of increasing and decreasing by 29, we're going to increase and decrease by 2.9. So one standard deviation below the mean would be 140.1. All right. Now I could go more than that, but really we were just looking for 140 and up. So I can create my shaded area now. And it's not going to be pretty because this is my big bugaboo, the whole physically producing writing on paper. So anyway, you could see that it's going to cover a lot more of the graph, right? And the rationale behind that is, if you're talking about averages from within a group, right? So I take 100 individuals and I find their group average. It's going to be in the neighborhood of 143. If I take another 100 individuals, find their average, it's going to be in the neighborhood of 143, and so on. It's going to eliminate all those extreme values that might exist if you went person by person. All right. This is talking about people, so you could have somebody that's incredibly underweight and somebody who's the opposite of that. So all sorts of different possibilities come into play. But if you work by averages, whatever you come up with is going to be a number that represents the entire group. It's going to necessarily eliminate extremes. So, in terms of the computation, not too bad, because it's going to be the same setup as before, normal CDF. $140 to infinity. Oh, I left myself not enough room. Fortunately, this app is a little bit nicer than the other one I use. So I got that going for me. 143 and 2.9. Poor quality, close parentheses, so I'm going to fix that. So I could actually copy paste what I did before and just make it 2.9. Now, that's one thing that people kind of like is a strong word, but they don't hate about this particular topic, is that there, in terms of the computation, there isn't really that much different from what we were doing before, except argument error. Oh, because I lost my comma for some reason. I mean, the some reason is I deleted it, but, you know. We're looking at about 0.850. All right. So conceptually, you know, you're looking at something that, you know, it's roughly 30 percentage points off of the previous answer, but conceptually it should make sense, because if you're thinking in terms of a group of individuals, if I were to tell you that I wanted to find an entire group of individuals whose average weight is in a particular interval, it's gonna, you know, it's gonna look and feel a lot different than it would if you had, you know, just going person by person. You know, it's kind of like it's tough, because the conceptual part of it doesn't really come through in textbooks and stuff like that. So the one thing I'd ask you to visualize is you're standing in the middle of a big crowd. Hopefully not these days, but you're standing in the middle of a big crowd, and I ask you to find somebody who has red hair. Okay, it's just one person who has red hair. Shouldn't be that hard, right? You know, like, amend your visual image to have nobody wearing hats or anything like that. So very easy to find somebody who's wearing red hair, who has red hair. Now, if I were to follow that up by saying, find 5 people grouped together who all have red hair. You're in a crowded room, 5 people all grouped together who have red hair. You might say, well, I mean, they'll stand out if they're all grouped together because they have red hair and they're all together. It'll be a little bit more obvious. But what is the likelihood that 5 people all having red hair are going to be standing right next to one another? Now, you can get into the whole thing of like, oh, they're all siblings and stuff like that. We're talking about the Weasleys, Easter egg right there. Give me any movie title that involves the Weasleys, and I'll give you 1 bonus point. But yeah, it's going to be a lot harder to find. And so that's what the central limit theorem is. It's a change in probability based on the change of conditions. So example 3, math professors have IQs that are normally distributed with a mean of 125 and a standard deviation of 1.2. The first example, one math professor is selected at random. Find the probability his IQ is greater than 127. This is not the central limit theorem part of it. So 125 and 1.2 are the big numbers. Oh, I don't know why I wrote 1.2 there. 126.2. 127.4. All right, 2 standard deviations up. They're saying 127 or better, so that puts us around right here. All right, so for A, that's normal CDF. $125 or better. 127 or better, sorry. With a mean of 125 and a standard deviation of 1.2. So here I'll take it from scratch. Second vars, normal CDF, 127, something big, go 500 this time, 125, 1.2. All right, so something bigger, make it 5,000. Same decimal, but even if it wasn't, I'm sure it would round. If when you get big enough, when your values get big enough, they generally tend to round anyway. So 0.0478. All right, so this is less than 5%. So, you know, it's borderline unusual. You know, so somebody with it in this population that has this characteristic, or these characteristics, would be considered statistically unusual. And, you know, with a high IQ, that's a good thing, I guess. The next one, normal CDF, still 127 to infinity. We learned that the mean is not going to change. That's still our mu sub x bar. The sigma sub x bar is just simply going to be divided by the square root of 75. The sigma is going to be divided by the square root of 75, which is going to give us the sigma sub x bar. I'm curious to see what that would be, so I'm just going to chuck that off on the side here. Oops, I hit the wrong thing. So we're talking about 1.139, so about 0.14. All right. So what I'm going to do is I'm going to overlay these values below. I'll do it in red. Yeah, that red. So 125, 125.14, 125.28, then 125.42. We're already above 3 standard deviations away from the mean. So this is going to be so far off into this territory here that its probability should be really, really minuscule. Right? So that's what we're getting at. The idea that, you know, like I just told you, that finding one person whose IQ is above 127 under those conditions would be unusual. Now I want to find 100 individuals, or let's say like a college faculty whose IQs are unusually high. So I made a slight adjustment here. This is saying 0. Your calculator is going to say something else, but it's going to say virtually 0. Because you're going to get something times 10 to the negative bazillionth power. All right. So we would say this is virtually 0 because we don't want to actually say it's 0 because it's not impossible, but it's so unlikely that it might as well be 0. And I accept that as a correct answer because my calculator gave that, but also that's what it is. You know, so that's entirely possible. So you'll get some disgusting scientific notation on your calculator. You could write that scientific notation, that's fine, or you could write virtually 0. Either way is perfectly